right. Can you see my screen?
Yep.
Okay, cool. So thanks for joining for this second NLP Breakfast session. So yeah, so we started a few weeks ago. Ideally, we would like to do it some kind of regularity, so every 2 or 3 weeks. So the goal of this meeting is to discuss either some papers regarding NLP or some trends regarding different models. So everyone is welcome to suggest a paper or to suggest a new presentation for next week's. And yeah, during the presentation, everyone is welcome to ask some questions and interact. Yeah. So for this week, we are gonna talk about language models. So we are gonna talk about this trend. So not a single paper, but the evolution in language modeling techniques. So just basically to put everything into context, so language modeling is a task which consists in predicting the next word from a sentence. So it's a conditional prediction. So based on the beginning of a sentence, we're trying to predict the next word. So this is already included in many everyday life products. So for example, in your smartphones, it can predict the next words, or in search engines, it can do auto-completions. But language modeling is also used in many different products like machine translation or speech processing and many more. So language modeling, so you're trying to predict the next word based on previous words. So if you call by some x's your different words, you're trying to predict the probability distribution over the next words, xt plus 1, depending on the previous words. And so an assumption that is usually done is the Markov assumption, is that the future depends only on a few words from the past. So here we define a window of n-1 words. So the probability distribution of the next word will depend only on the past window. So the first way to do this, to calculate this probability, is to use the Bayes formula. And so we have like this formula, so the probability of the joint distribution from the whole window plus the next word, and the probability of the previous window. So a first way to approximate this probability is to just use some counting measures. So we will only count in a big corpus the number of times the whole window plus the next word appear divided by the number of times the window appears. So this has a few problems, so especially sparsity problem. So if you look at this, so the numerator, for example, if the window is large, this set of tokens might never appear in your corpus. So this might be 0, even if the sentence could be likely. And more important, if the window never appeared, this can be 0. So we could even not be able to compute this counting. And besides sparsity, you also need to store all these Ngram counts, which can be really huge, especially if n is large. And the thing is that you would prefer n being large because it gives more context to your prediction. So you have this context size issue. So to avoid this problem of sparsity, so the direct application with neural networks is to so still use the fixed size window. For example, we take 4 tokens. We take their word embeddings, so they can be pre-trained, and you just concatenate these embeddings, and then use a projection, a linear projection, to get the distribution of the next words. So this solves the sparsity issue, and also the storage problem, because we decrease the dimensionality. But still, the window remains quite small, because if you enlarge a window, you will end up with a gigantic concatenated vector here, so you will still have some issue. And another issue is that here the matrix multiplication will be different for every word, and we would like to have some parameter sharing between words. So this is why recurrent neural networks were useful for language modeling, because in this setup of RNN, so you don't concatenate the word vectors, so you can have an unlimited, in theory, window size to get your language model. So there are so many ways to use language model, but one of the way to visualize what it can do is to generate text with language model. So at each time step, the language model predicts the distribution of the next step. So you can think of a language model as a way to compute probabilities for whole sentences. So this probability will be the product of all the prediction probabilities. So one way, so if you want to generate a probability with the highest, a sentence with the highest probability, in theory you should compute all the possible sequence of tokens, and then compute the product of probabilities. But this is a huge combinatorial problem, so this is not done. And usually, so what is done is either doing greedy decoding. So at each time step, we use the first prediction. So this provides some good decoding text, but this would be suboptimal because you will not have a sentence with the highest probability. And another way of decoding is to using beam search. And so the beam search algorithm functions step by step, and at each time step, each decoding step, we keep track of the k most probable prediction. So here, as an example, I have used a visualization tool from OpenAI, so which is based on the GPT-2 transformer. So it's also based on the implementation from Hugging Face. So thanks, Victor, for this implementation. And so here, I just entered Feedly in the. So maybe we can even go on it.
You're casting on your tab.
Oh.
But they may see.
Yeah, they see it. Can you see the Allen AI page?
Yes, we can see it.
Yeah. For example, here I just start with Feedly, and then you can choose all the next words. So it's pretty amazing, but it's really relevant. And you can build some highly likely sentences. And it's also a very fun tool to play with. So one of the issue we have with LSTM-based language model is that we use some word embeddings that were pre-trained from huge corpora of text, but these words, so we have one embedding for every word, but a word can have different meanings depending on the context or depending on the registry we use it from. So there is a difference between the type of a word, which is the word itself, and the token, which is the word in the context. And so there has been some work to bring the context and to add it to the pre-trained word embeddings. And so in this work, so this was one of the early work on contextualized word embeddings. So this was in the setup of name entity recognition. So in this paper, so the author wanted to not only use pre-trained word embeddings, but to have some contextualized word embeddings. So what they did is, instead of just using their dataset for name entity recognition, they used huge datasets to train some language models. And using these language models, so they used one forward language model and one backward language model. So it just changes the direction we learn on. And so when you concatenate these two vectors, you actually get a representation of the word in context. So in this paper, so they use a regular LSTM model to do name entity recognition, and they add the contextualized representation. They concatenate it to the word embeddings representation, and so this produced some better results. But however, we could think that contextualized word vectors should be sufficient. But they found that if they only use contextualized word vectors, the scores are not as good. So they had to combine both, so pre-trained word vectors and contextualized word vectors. So then came another innovation. So Elmo brought just a few layers on this. So it's basically the same idea. So bringing some contextualized word vectors, but it's just that the language model representation is a bit different. But you can see here that it performs a little bit better on name entity recognition. And the difference is that so the language model has several layers, and just as in computer vision, we saw in ImageNet and other competition, we saw that different layers captured different level of information. So this is similar in natural language processing, and lower level of language model will capture more information for lower level NLP task, like NER or syntactic NLP task. And higher level representation would be better for higher level tasks like sentiment analysis or question answering. So what they do here is that instead of just taking the last layer of the language model, as they did in the previous paper, they learn an average of all the different layers of the language model. So here is the average that they take. So they average over the different layers, and they also learn a parameter which will say if for this task is Elmo necessary necessarily good to produce good results. And so you can see here, so results on different data sets where they outperform state-of-the-art. So here in question answering, especially in coreference and NER also. So Elmo has become like one of the leading pre-training model that we can use in addition to word embeddings like word2vec or Glow. Another similar paper in the subject was the ULM fit from Sebastian Rieder and Jeremy Howard. So this was a really similar setup. So you pre-train a language model on huge data sets, but here they wanted to apply it to text classification. So here, after language modeling, they would take a lot of care on what they do next on the text classification task. So they have a lot of care on the language model fine-tuning. So you fine-tune your language model on the task, the specific task that you want to transfer the knowledge on. So what they did for this fine-tuning, they included a lot of like different learning rates for different layers, or gradual unfreezing for fine-tuning. So they started by unfreezing the last layer, fine-tuning the last layer, then fine-tuning the different layers from top to bottom. And at the end, so they learn the last layer, which is the classification layer. And on this image, so they show the importance of pre-training on the IMDb dataset. So IMDb dataset, this task is to classify movies based on reviews. And so you can see that if you train the same model from scratch, it will need a lot of more training example to perform well. Whereas using ULM fits with fine-tuning, so semi-supervised means you fine-tune the language modeling on the LMDB datasets. You see that even with 100 reviews, you already have the same result as with 20,000 reviews with a from scratch model. So this is really great for few shots classification. And here on this image, so this was an experiment we did a few months ago. So we just applied the same methodology but to another dataset. So it was an Amazon reviews dataset, and we saw that even with a few hundreds labeled reviews, the model was able to make very good prediction. So this means that the language modeling task is able to learn already quite a lot from the language, so that the classification part just has to take this representation and find some classification layers. So what ULM Fits gave to the community is that it was made to be available for everyone, and so it was made to run on just one GPU and with a relatively small model. So everyone can run on FastAI such a model and achieve good results. But then from that point, a few huge corporations made some large-scale experiments, and they outperformed results on many tasks. So there were the two GPT models from OpenAI, and especially the recent BERT model from Google. So all these three models, they all leverage the power of transformers model. So transformer models are also a recent trend for language modeling, which is another level of magnitude of scalability. So, so in last NLP Breakfast, we talked about transformers. So maybe just a quick recap. So transformer was introduced by this paper, Attention is All You Need. And the motivation behind it was that RNN or LSTMs are fundamentally hard to parallelize because they are essentially sequential. And still, using LSTMs, so LSTM were made to improve how long we can go in the past to have some information, but actually still like attention layers were necessary to get long-term dependency. So the fundamental motivation behind transformers is that if we still need attention layers to get long-term dependencies, why not just use attention layers? And if we just use attention layers without any recurrent setup, we can then use some GPU optimization to speed up the training. So here is the architecture of the original transformer model. So in the original paper, this transformer model is used for machine translation. So you have an encoder and a decoder, but here we will just look at the encoder because that's what we are interested in for language modeling. So so transformers so uses attention layers and only. So just to recap, attention is a computation between a set of keys, queries, and values. And self-attention is a setup where all these are the same. So we take the words in the sentence or the text, and we make them attend to each other's. So this is why it's called self-attention. And because we want words to attend to each other, maybe in different ways, the paper introduced multi-head attention, where so it's just in parallel several attention layers to let the words attend differently with each other. And so if you look at the encoder layer, so this is a series of multi-head attention and then feed forward with some normalization and residual connection between them. And this block is repeated 6 times. So this is all for the encoder. And because we're not in a recurrent setup, so they add a positional encoding to keep track of the sequential order of the words. Yeah. So this was I think at the end of 2017, and at the end of last year, so another paper from Google AI was for BERT. So this model has become one of the mostly talked about language model and NLP model in general. And so this model was trained on huge amount of data, like really much more data compared to other language model. So so the innovation given by this paper is that they don't use language modeling in the exact same setup as before. So before it was predicting the next word based on previous words. But here they argue that they actually don't need this order. They just want to be able to predict words, whether you use past or future context. So here they really use a bidirectional model. And here the task is not to predict next words, but the task is to predict some random words that they mask. So they mask about 15% of tokens in the dataset, and the task is about predicting what are these tokens. And the second task they train on is similar to next word prediction, but they do it at the sentence level. So they take one sentence, so the man went to the store, and another sentence, he bought a gallon of milk, and the goal is to predict whether the second sentence happens after the first sentence or not. So here is an image from the paper comparing different architectures. So with the Elmo architecture having one forwards language model and one backward language model, compared to the BERT having an inherently bidirectional layer model.
So if you're not predicting the next word, like how would you use it in machine translation, for example, if you're trying to do that task?
Sorry?
So if you're not predicting the next word, like how would you use BERT to do machine translation?
Oh, I think this would be in the decoder parts of the machine translation parts. Because here, so this is used for the training of the language model.
Okay.
So at the end of the encoder part, you get a representation, and then maybe for the decoding part, you will use a regular next word prediction.
Okay.
Yeah. And so to finish this overview, so language modeling is a really exciting field because so it seems like we are in a moment in NLP which is a bit similar to the imaginate moments of computer vision. So we have a lot of different pre-trained models which become available. So they are built on more and more data, more and more tasks, and it seems that so the promise of language models is to enable transfer learning. So ideally, if we want to achieve like higher level of natural intelligence in NLP, we would like to have models which can learn across different domains. So if you have a model which learn on text which are about sports, for example, you would also like it to be performant in text which deals about politics, for example. So you want a model which can perform well over different domains. Because even if you take a data set, so right now in the research community, most people rely on a data set. So they want to increase the state of the art on a data set. But then the model which are performing well on data sets, it's not straightforward that this model will also perform well on another data set. So language modeling is like a promise for this, and also to learn across tasks. So multitask learning is also a very promising field for this. And another dimension is the multilingual dimension. So if a language model, if such a transfer learning model could be done across languages, so such a model could learn across domains, datasets, but also different languages. So this is, I think, really exciting to maybe in the future use language models as general encoders, and then we could use these encoders to give information to specialized learners. Because right now everyone working on machine learning for specialized datasets, they use some specialized pipelines, but they could benefit from generalized pre-training embeddings. So what would be ideal is to use these language models to give extra information to experts, narrow classifiers or regressors. But there are a few limits to this. So here are two of the limits. So one is catastrophic forgetting. So this is especially true in the multitask setting. So you train on a task, and then you try to train it also on another task, but you don't want the model to forget what it has learned on the previous task. So this is really challenging. I think, Victor, you have worked a lot on multitask learning. And another issue is that so you might have heard of the OpenAI GPT paper. So they released a paper with a language model that they said was so good that they don't want to release the model itself, because they think that it could be used in malicious ways. So especially in the spread of misinformation. So if you have so remember when we played with the language model from GPT-2, so it's really easy to generate fake content, and so this could lead to a lot of fake news and other kind of misinformation. If you think of financial markets, they rely a lot on news. Imagine that you can manipulate news. You could manipulate also the market. So that's also really a really huge problem. So so thank you for joining this presentation. So here are a few resources to use for language models. So as usual, this Stanford NLP course is really great. So I really encourage you to take these lessons. And so there are a few resources for papers, especially the annotated transformer. This was from, I think, Harvard NLP. So they have a notebook which explains the transformer like really thoroughly in every layer. And also the GPT-2 Explorer, which allows you to play with the language model decoder. Thank you very much. And so if you have any question.
So on that slide, you showed like the increase in training times. What about the inference time performance? Is it also getting more and more heavy with new models, or is it not?
I don't really have experience on this. Maybe Victor, for inference time?
In terms of inference time, it's it really depends on the size of the model. I know that BERT is quite expensive in terms of inference time. GPT-2 also, but it definitely depends on the size of the model. But I wouldn't say that's really a burden, depending on your use case. If you are already able to use some LSTM-based language models today, switching to a transformer-based language model is not that much of a burden. But definitely in terms of training, since you're training in a huge data set, most of the people can't afford to train a language model on such a huge data set.
Do you have an order of magnitude for the speed, like in terms of tokens per second or some kind of measure for decoding part?
I don't have it in mind. That's a good question.
Yeah.
Sorry.
Yeah, that's okay.
But another thing, maybe just to complete the discussion on language models, and I think that is something that they show on the last GPT-2 paper, so the thing that came out months ago, is that you can think as language modeling objectives as a superset of everything in NLP, at least almost everything in NLP. What they show in the paper is that they perform really, really well in a zero-shot learning setting on different tasks, such as machine translation, summarization, and the examples are pretty incredible without actually functioning the model for machine translation or for summarization. So more generally, you can think of language modeling as a superset of everything.
Okay. So did they get state-of-the-art results or competitive results on those tasks?
I don't think it's state-of-the-art results, but when you
But
look
still
at the
very
example, when you look at the example, it's like pretty convincing. I mean, without even fine-tuning the model for that, without even telling the model what is summarization, what is reading comprehension, what is machine translation, the model is actually able to learn to do this kind of thing. So that's pretty impressive. Yeah.
Right. Thank you everybody for joining. This video will be on the Feedly blog, and see you in 2 or 3 weeks for the next episode.
Yeah.
Okay.
Thank you very much.
Thank you.
Have a good
Bye.
day.
Thank you. Bye.
Bye.
Très bien. Comment on éteint la vidéo? C'est le bouton aussi.